Hi everyone. In this work, we explore visuotopic organization of deep neural networks using the wire-length minimization hypothesis. Neurons in the cortex have a distinctive topographic organization where nearby neurons in the cortex have nearby receptive fields, forming a map of the visual field. This can be nicely shown in these images here, where neurons in the cortex are colored according to the receptive field location. If we look at the polar angle map, we can clearly see that the map repeats multiple times with each repetition corresponding to a visual area. One hypothesis that has been very successful in explaining organization in the brain is the wire-length minimization hypothesis. Simply stated, the hypothesis states that wires, axons, and dendrites are expensive to build, and there is high metabolic cost of long-range connections, so to conserve resources, the total wire length should be minimized. We ask the following question: what kind of visuotopic organization emerges when we arrange the units of a deep hierarchical network on a grid such that the total wire or distance between connected units is minimized? We do the following. We construct a network of n units. The network has L layers, example 4 in this picture here. Each layer connects to the previous layer. We can construct a different network by varying the number of layers, number of units in a layer, and the number of units each unit connects to, or the filter size. Then we say, let's arrange these n units on a grid with n location so that the total distance between connected units is minimized. For example, if we take a unit from each layer, the red layer, yellow layer, green layer, and cyan layer that are connected together, and place them on the grid, we can clearly see that this arrangement has a lower cost than this arrangement. We don't do this only for 4 units, we have to do it for all the units in the network. This is an NP-hard problem. For example, if you have only 50 units, you're going to have 50 factorial, or 3 times 10 to the 64 possible arrangement. It's a non-convex optimization, so how are we going to solve this problem? We're going to solve this problem with simulated annealing. But first, let's try to formalize it better. We say for each arrangement of unit on the grid, let's call this arrangement C, there is a cost E defined as follows. For 2 units I and j in the network, the cost will be Ai j dij, where Aij is an element of the adjacency matrix. It's simply 1 if units I and j are connected, and 0 if units I and j are not connected. And dij is the distance between units I and j on the grid, and you sum over all units I and j. So we're going to start with units randomly arranged on the grid. We're going to compute the cost. This is a cartoon of the cost landscape, and the red dot is my the cost of my state. We're going to pick a new state by randomly swapping 1 or more units. This is now the yellow dot. Then we're going to see if the new state has a lower cost. If this is the case, like what we see here, then we're going to accept it. But if the new state has a higher cost, then we're going to only accept it with a certain probability. So now let's see what happens when we map a purely feed-forward hierarchical network. Let's look at a network with 4 layers that has 630 units and filter size is 2 by 2, stride 1 in all layers. If we place the units of this network on a grid and colored those units according to their layer, we see that there is no clear organization by layer. Now, let's look at the visual field organization. To do so, we're gonna introduce an input layer and connect it to the first layer through a filter. It's important to stress here that the input layer is not part of the optimization, but rather a way that allows us to assign a receptive field location for each unit in the network. By knowing which input units each unit in the network connects to, either directly or indirectly, we can assign a receptive field for that unit as the center of its input units. Now, if we color the input layer according to a polar angle, we can clearly see that we have a very nice map. It goes all the way from green to yellow. If we color it according to the eccentricity, we see that we have very nice center to periphery organization. But most importantly is that we have one visuotopic map. So we ask the following natural questions. Does this result depend on the filter size? This is a network with a bigger filter size. Again, we see that there is no clear organization by layer, and we still have one visuotopic map. So the answer is no, it doesn't depend on the filter. Does the result depend on how deep the network is? Let's look at an 8-layer network that has 1136 units and look at its organization by layer. The layers from different, the units from different layers are actually still mixed together, and we still have one visuotopic area. So the answer is that the result don't depend on the depth of the network. Does this result change if we add more channels at each layer? For the sake of time, I will not dwell into this, but the short answer is this doesn't seem to be the case. We can ask, does this result depend on the stride? Now, to make a point, I'm going to give you an extreme case where we have a 4-layer network with filter sizes 2 by 2 and stride 2 in all layers. So we have non-overlapping filters. And as we can see, we don't have any visuotopic organization. So the answer is that yes, the result actually depends on the stride. Let's try to get some intuition of why do we get such a result. Well, units that are connected will be placed together to lower the cost. In a feed-forward network, connected units in different layers have nearby receptive fields. So units with nearby receptive fields are going to be placed together. Now, another point to pay attention to is that even though there is no direct connections between units in a layer, nearby units actually share connections, so they have similar connection, and so this pushes them to be placed nearby on the grid. When the stride exceeds the filter size, this is no longer the case and you lose the smoothness of the map. So our first key result is that purely feed-forward hierarchical networks only form one visuotopic map, and in the case of non-overlapping filters, no visuotopic map emerges. Now we ask, how do we get multiple areas? Well, we know that the brain has horizontal connections, so let's try to add horizontal connections in the layers, and we can actually vary them by layer. But let's see what happens when we add long horizontal connections in all the layers. Suddenly we have a strong organization by layer, we have multiple maps, and we have a clear one-to-one correspondence between a layer and a map, but it's a non-biological retinotopy. And to give you some intuition of why do we see such a result or such an organization, well, let's look at our cost, and we divide it into two parts. One part that's coming from the between layer connections, and one part that's coming from the horizontal connections. So when the number of horizontal connections is very large, this term in the cost becomes large and it dominates. So to lower it, you place the units in the same layer closer together. So that's why when you when we have long range connections in the layers just basically kind of the units on the layer just sit together. So we ask, how do we get something that looks more brain-like? When one idea is to have the horizontal connection length vary by layer. For example, we can have the early layers have long horizontal connections and later layers have shorter horizontal connections. Well, this idea we got inspiration from the brain. If you look at the brain, you see that you have one large area and then you have like smaller areas wrapping around it. So by putting less horizontal connections in the top layers, we're giving them enough flexibility to be able to wrap around the lower layers that have longer horizontal connections. So what do we see when we actually construct such a network? Well, now nicely we can see that there is signatures of multiple maps emerging. We see that we have a nice upper and lower visual field division, and if we take these borders and put them on the other maps, we can see that we have very nice fovea to periphery organization. And if we look at the bilayer organization, we have a nice organization by layer, with the first layer that has the longest connections contributing mostly to my center or largest map. So brain-like organization is beginning to emerge when we're adding horizontal connections in a certain way. There is so many ways to construct deep neural network. There are so many things you can vary, like the stride, the filter size, the layers, so on and so forth. The parameter space is very large. What we try to do is to broadly characterize some qualitatively different solution that exists in this space, guided by intuitions and inspiration from the brain. So to summarize, we basically found that when we have no horizontal connections, like only feed-forward, for example, connections, we have one area. When we have long horizontal connection in all layers, we have multiple areas but non-biological retinotopy. Of course, you can guess by now that if you have short horizontal connection in all layers compared to the in-between layer connection, you're going to still have one area. But then there is this large area where you're going to have a huge number of solutions. And what I gave you is one recipe to obtain solution with a brain-like motif. But it's not unique, and there is actually a family of solutions with these motifs. So what we did is that we explored how different visual field connectivity networks map topography under constraints of minimal wiring. We found that there are three factors that affect the resulting organization: the horizontal connection length, the in-between layer connections, and their relationship to the layer size. So we mainly found that feed-forward hierarchical networks alone do not reveal separate hierarchical areas. Horizontal connections are required to reveal a hierarchy of visuotopic maps, and ratios between horizontal feedback connections and layer size jointly contribute to create a brain-like organization. So deep neural networks don't have topography, but do have a connectome. Under constraints of minimal wiring, we can reveal the topography implied by these connections. So this approach offers a normative perspective of how to map the implicit topography of deep neural networks, providing an additional length into biological networks. Thank you so much.